Hello and welcome to this video on forces. Specifically, we're talking about systems or connected objects. Today we're going to talk about connected objects in a way that's slightly different. Instead of having them be connected over a pulley, we're just going to have them connected in a row like this. So we have three blocks connected. We have an 8 kilogram, a 5 kilogram, and a 10 kilogram block. They're all connected and they're being pulled by a force that is exerting 100 newtons. This could be from a pulley or it could be just you, but for right now it comes from somewhere. What we want to know is several things. We could ask about the acceleration of the system. We could ask about tension in the two wires here. And in order to figure out either of these, you have to kind of understand how this works or how we think about this. Some assumptions that we make first. First, we're still assuming that the strings are massless and we're going to ignore friction for the time being. Adding in friction we'll talk about later. So to start, let's talk about the acceleration before we talk about the two tensions. Because these blocks are all connected, because they're all moving as one, we can treat them as a single object or a single mass in a system. So instead of focusing on three blocks with a total mass of 23 kilograms, we just say that there's one mass of 23 kilograms. At which point, finding the acceleration is very easy. Sum of all forces in the x direction equals max equals that 100 newtons. Or in other words, 23 times A equals 100. Or A equals 4.35, rounding, meters per second squared. And that's it. That's all it is. It's fairly easy. Finding the tensions, however, gets a little more complicated. So let's back this up and take a look. So if we want to talk about the tensions, we need to look at these not as a single collected system. What we need to do is we need to look at them as individual objects. So we need to draw free body diagrams for each. So let's start with the 8, the 5, and the 10. The 8 is the easiest. There's going to be a tension force pulling this way. And I'm going to even call it tension 1. We're going to have normal force going up and gravitational force going down. And that's it. And because we have a net force to the right, we can find the acceleration, we can find the mass. Object 2 is slightly harder because not only do we have tension 2 pulling to the right, we have tension 1 pulling to the left. Now, these two values will be the same, but they are different. They are pointing in opposite directions. You'll still have a normal force. You'll still have force gravity. And then even more, I can go ahead and label all these as being equal. The 10 kilogram block is the last one, and it's going to look almost identical to the blue, but instead of T2 being on the right, it's going to be on the left. And the 100 newtons is over here. Now, how do we find our tensions? Well, I already found the acceleration of the system. We said, based on our calculations, that it was 4.35 meters per second squared, which means that this block is accelerating at 4.35 meters per second squared, as is this one, as in this one. Because the system is accelerating at that rate, each object in that system is accelerating at that rate. So all I need to do is write down my sum of all forces. My sum of all forces in the x direction equals max equals ft1. And for the red, that's all there is. I don't even have friction right now. Again, we'll get to that later, but that's all there is to it. So solving this becomes eminently easy because my force tension is just going to be m times a for this one. Because it's the only force acting. So 8 times that 4.35 equals T1. Or T1 equals 34.78 newtons. And you'll notice here that the number is slightly different because I didn't use the rounded number. I plugged the full number in my calculator. I can continue this trend on and move on to the blue, or the second mass. Again, we're only going to focus on x because y is solved and we don't have to worry about friction. So my sum of all forces in the x direction equals max. In this case, I have force T2 minus force T1. But the process is still the same. I know the mass, I know the acceleration, and I know T1 from here. So 5 times 4.35 equals ft2 minus the 34.78 I had here. If I rearrange and solve, I get 56.52 newtons. And there you have it. That's how you can find the tensions. But step one, look at it at the large scale, look at it at the system level. Step two, break it down. Look at it at the smaller level, the micro level. The ability to pivot between looking at the large scale, treating it as one object moving with one acceleration, and looking at it as multiple different objects and pivoting between the two allows you to get a lot more information and a lot more thought about problems. With that said, let's take a look at one you can try on your own. It'll be the same problem, just with friction, and then we'll give it a try. Okay, here we go. So this time it's the exact same problem, exact same setup. There's 100 newtons pulling these three connected blocks together. The only difference is this time there is a frictional force acting, and the frictional force has a mu value, or mu kinetic value for the moving blocks of 0.42. We're assuming the blocks are moving. As they move to the right, what is the acceleration, and what is the tension in each of the wires? A hint to start. You're going to do the exact same process. Look at the big scale, find the acceleration, then look at the small scale, find the tension in each of the individual wires. But the friction needs to be factored in, both on the large scale, where it'll be affecting all objects as if it was one object, and at the small scale, affecting each object individually. Go ahead, give it a try, check back when you're done. Okay, here we go. We start with the black, which is where I solved the entire problem through. I started by with my force normal, and then getting my force, getting my mg value for that, plugging that in, getting fa minus ff, or more accurately, my acceleration for the entire system simplifies down to 0.2318. If I go over here and plug that in, solving for red, I run through the entire problem again, getting my tension, solving for my tension. In this case, because I know friction, I know normal, I know force gravity. Plugging in my values gives me 34.78. It's not much bigger than what we had previously, but it is slightly bigger, which makes sense. There's a relatively small acceleration here. The value will be smaller, or the difference will be small. I go through, do the same process again for the blue. You'll notice that I have tension and friction pulling it back, so I have minus FF minus T1 here. Again, solve for FT2, plug in my numbers, including the 34.78 I got from the previous problem, and I get 56.52 newtons. This isn't the only way I could have solved this problem. I could have used a free body diagram for 10, the green here, and solved it through that way, at which point T2 and the force applied, the net force would be the only difference between the two values. I could have gone through and solved for, or I could have treated this entire section here circled in green as a single object, at which point T2 would be the only force left out on the right. T1 would be an internal force at that point. It's internal to the system. It doesn't have any effect on the overall effect. Some notes. First and foremost, if we looked at the normal force for this, which I said is m times g, it's really just m1, m2, m3 added together, which gives me my total mass times g. Or, in other words, the sum of my normal force for this one, my sum of my normal force for this one, and my sum of my normal force for this one will equal my total normal force. The same is true for my weight, m times g, or my frictional force. The friction here plus the friction here plus the friction here would all add up. you can look at the scale between large and small, and going back and forth between them becomes a very useful skill, and knowing how that works goes back and forth. If I was asked to solve for anything for this value here for the green, I already know the frictional values here, so I can find the frictional value here based on the difference from over black values. Next, notice that how while this is 100, this is 56.52, and this is 34.78. It gets smaller as you get farther away from the source of the pole. Well, in this case, that's because this black line, this force applied over here, this 100 newtons, has to pull the 10, the 5, and the 8. Whereas T2 only really has to pull the 5 and the 8, and T1 only has to pull the 8. The amount they have to pull and provide that acceleration to decreases as you work your way farther and farther back. Anyways, thanks for watching. Have a good one.